Welcome to this explainer. Today, we're diving into a genuinely fascinating challenge, right at the intersection of environmental science and cutting-edge web technology. We're going to tell the story of taking something completely invisible, wind, and turning it into an interactive 3D digital twin. You see, environmental impact assessments, or EIAs, are absolutely crucial for figuring out how a new development is going to affect an ecosystem. But traditionally, they have a huge communication problem. They rely on static tables and super technical reports to explain these dynamic, invisible forces, making it incredibly difficult for everyday non-experts to actually grasp what's going on.
Picture this. You're a local citizen sitting in a town hall meeting, and a developer hands you a spreadsheet packed with thousands of numbers to explain how a new factory's emissions are going to blow across your neighborhood. It's basically meaningless, right? So the million-dollar question is, how do you actually show a community the exact path a gust of wind is going to take next year? How do we take that heavy, complex data and turn it into intuitive 3D maps that literally anyone can understand in a second?
Which brings us to Section 1, the big data bottleneck, or as I like to call it, the weight of the wind.
To really appreciate the solution here, we've got to wrap our heads around the massive scale of the problem. Capturing air data isn't just about sticking a single sensor in the ground. Air takes up a massive volume, changing horizontally across the terrain and vertically up into the sky, constantly shifting over time. The researchers in our source material looked at a sample area of 13 by 13 kilometers. Within that space, they collected data at grid points spaced every 100 meters. That is 17,161 individual data points. Now multiply that across 7 different height levels, going all the way up to 200 meters. And they didn't just take one snapshot, they collected this every single hour, for an entire year.
When you tally all of those grid points, heights, and hourly updates up, you're looking at a whopping 4.45 gigabytes of data. And remember, that's just to visualize a single year's worth of wind and air quality for one specific area.
And right there is where we hit our big data bottleneck. The whole point of building this digital twin is public accessibility, meaning it has to run smoothly on a standard web browser over a normal internet connection. If you try shoving 4.45 gigs of raw vector data into a browser, a user would be sitting there staring at a loading screen for nearly 15 minutes. That completely defeats the purpose of an accessible tool.
So let's move into Section 2, packing wind into pictures, also known as the PNG disguise.
We obviously can't send the raw data as is. So the engineers had to find a clever workaround. How do you squeeze a year of wind into a web browser? We need to compress this immense volume of information without losing any of its vital scientific accuracy. You can't just toss out data points, because then the environmental assessment would be flawed. We essentially needed a perfect, lossless suitcase for the wind.
Well, here is the brilliant turning point of the whole journey. Instead of sending clunky spreadsheets of numbers, the researchers mapped the atmospheric concentration values directly into the pixels of a PNG image. Seriously, they took the raw grid data and encoded it right into the red, green, blue, and alpha channels of the image format. So you're no longer transmitting a massive database, you are quite literally transmitting a picture of the data.
Now, why use a PNG specifically? Well, there are 3 massive reasons. First, lossless compression. This means every single scientific value is perfectly preserved. Not one decimal point gets lost in transit. Second, PNGs are universally adopted across the web, making them incredibly easy to transmit. But the third reason is a real game changer. PNG images are directly compatible with the computer's graphics processing unit, or GPU. There is absolutely no extra heavy decoding required when that file arrives at the user's computer.
All right, Section 3, animating the airflow, or the GPU magic show.
Once this tightly packed PNG suitcase arrives at the user's browser, how do we unpack it and bring it to life in 3D? Traditional 2D mapping techniques just mix flat images together, which completely falls apart when you add a 3D height axis and let users rotate the camera. Instead, this system relies on GPU acceleration. It receives the wind field data, binds it straight to the graphics card, allocates memory for thousands of floating particles, and rapidly calculates their next positions all in parallel. It is basically a high-speed computational magic show happening right on your graphics card.
To make the wind's direction and speed intuitively obvious to the human eye, the system creates these things called wind flow markers. By saving the past positions of each particle in the memory, it essentially drops breadcrumbs. The current position is the head, and the past positions form a tail.
This after-image effect makes it incredibly easy to see exactly how fast and in what direction the air is moving at any given second.
Taking a quick step back, we can trace the complete journey of our data. We start with those massive, clunky vector fields on the left. We pack them tightly into a PNG format to shoot them instantly across the internet. Then, the user's GPU unpacks it, calculates all the particle movements, and renders a stunning, interactive 3D visualization right inside the web browser.
Next up, Section 4, Tracking Pollutant Dispersion and the Real-World Impact. Predicting clean wind is amazing, but it's really only half the battle. To truly understand an environmental impact, we have to look at what that wind is carrying. And here is the spectacular climax of this tech: instantaneous wind intensity and direction mapped right over the digital twin topography of Jeju Island in South Korea. The varying colors and the flow of the markers immediately tell you how the natural landscape channels the air. It's beautiful for sure, but more importantly, it's instantly readable. Building on that exact wind flow, the system can then apply spatial dispersion models. So instead of just showing wind tails, it predicts particle generation and simulates how actual pollutants will diffuse over time based on the specific type of pollution source. You can actually sit back and watch over a simulated full year exactly how a cloud of odor or emissions will spread across this 3D digital landscape.
Which leads us to our final part, Section 5, Empowering Public Participation and Bridging the Gap.
So why does all this complex GPU math and PNG encoding actually matter? Well, it brings us right back to the humans this technology is meant to serve. The core takeaway from this explainer is that visualizing the invisible fundamentally breaks down communication barriers for non-experts. When community participation is essential for sustainable development, you just can't expect everyday folks to read multi-altitude atmospheric sensor logs. You have to translate that data into a language everyone instinctively speaks, and that's sight.
The researchers behind this digital twin system really hit the nail on the head when they said, transforming airflow data into intuitive visual narratives fosters a better understanding and greater engagement among diverse stakeholders. By fusing real-world sensor data with interactive web-based 3D environments, they are creating a far more participatory, transparent, and fair assessment process.
We've seen how packing data into pixels can bring the invisible wind to life right on our screens, empowering communities to literally see the future of their environment. It really makes you wonder, if we can capture and render the very air we breathe, what other invisible forces shaping our world could we finally see by building a digital twin? Definitely something to think about. Thanks for joining me on this explainer, and keep exploring.